Imagine trying to understand a vast and intricate machine. A machine so complex that it seems almost impossible to decipher at first glance. You might begin by taking inventory of its fundamental components, meticulously cataloging each part, no matter how small or seemingly insignificant. Next, you would figure out how these components connect, how they fit together to form a cohesive whole. And then, you would seek to understand the rules that govern their interactions, the principles that dictate how each part influences the others. This is precisely the ambition of the Standard Model of particle physics. It aims to be the blueprint for understanding the universe at its most fundamental level. It's our best attempt to categorize and explain the universe's most fundamental building blocks and the forces governing their behavior. These building blocks are the particles, and the forces are the interactions that bind them together. The Standard Model, developed in the latter half of the 20th century, is a triumph of scientific collaboration. It represents decades of work by physicists from around the world, each contributing a piece to the puzzle. It's a testament to the power of human curiosity and ingenuity in unraveling the universe's deepest secrets. The model has been refined and tested through countless experiments, each one bringing us closer to a complete understanding. This model describes a universe teeming with particles, constantly interacting through a delicate interplay of forces. These interactions are what give rise to the phenomena we observe in the world around us. These particles and forces are the very essence of everything we see and touch, from the smallest grain of sand to the largest galaxy. They are the building blocks of our reality, the fundamental ingredients that make up everything in the universe. Just as the periodic table organizes chemical elements, the Standard Model classifies fundamental particles into distinct categories. These include quarks, which combine to form protons and neutrons, leptons, which include electrons and neutrinos, and bosons, which are the force carriers. Each particle type plays a specific role in the grand scheme of the universe, contributing to the tapestry of forces and interactions that define our physical reality. Quarks and leptons make up matter, while bosons mediate the forces that act upon them. In the following sections, we'll embark on a journey into the heart of the Standard Model. We'll delve into the intricacies of these particles and forces, exploring how they come together to form the universe we know. We'll explore the strange and wonderful world of fundamental particles, uncovering their unique properties and behaviors. We'll unravel the nature of the forces that govern them, from the strong force that holds atomic nuclei together to the electromagnetic force that governs the behavior of charged particles. And we'll glimpse the profound implications this model has for our understanding of the universe and our place within it. The Standard Model not only explains the fundamental structure of matter, but also provides insights into the origins of the universe and the nature of reality itself. As we journey through the Standard Model, we'll see how it has shaped modern physics and continues to drive new discoveries. From the Higgs boson to the search for dark matter, the Standard Model is at the forefront of our quest to understand the cosmos. So join us as we dive deep into the world of particle physics, exploring the fundamental particles and forces that make up our universe. Together, we'll uncover the secrets of the Standard Model and gain a deeper appreciation for the intricate and beautiful tapestry of the cosmos. Few forces are as familiar and yet as mysterious as electromagnetism. It is a fundamental force of nature that governs many aspects of our daily lives, often without us even realizing it. It's the force responsible for the familiar phenomena of light, electricity, and magnetism. From the moment you flip a switch to turn on a light bulb, to the way magnets stick to your refrigerator, electromagnetism is at work. It's the reason your computer screen glows, the reason magnets attract or repel, and the reason you can see these very words. Every electronic device you use, from your smartphone to your television, relies on the principles of electromagnetism to function. Electromagnetism is a long-range force, meaning it acts over vast distances. This is why power lines can transmit electricity over hundreds of miles, and why satellite communications can send signals across the globe. It's carried by a fundamental particle called the photon, a massless particle of light that travels at the speed of light. Photons are the carriers of the electromagnetic force, enabling it to act over such large distances. Photons are constantly being exchanged between charged particles, like tiny invisible messengers carrying the force of electromagnetism. This exchange is what allows charged particles to interact with each other, even when they are far apart. Think of a game of catch with a beach ball. Each time you throw the ball, you impart a little push to the other person. This is a simple analogy for how photons mediate the electromagnetic force. Each time you throw the ball, you impart a little push to the other person. Similarly, when two charged particles exchange photons, they exert a force on each other. This force can either pull them together or push them apart, depending on their charges. Similarly, when two charged particles exchange photons, they exert a force on each other. If the charges are opposite, they attract each other, pulling closer together. If the charges are opposite, they attract. This attraction is what allows magnets to stick to metal surfaces and what holds the electrons in an atom close to the nucleus. If they are the same, they repel. This repulsion is why like poles of a magnet push away from each other and why electrons in an atom don't collapse into the nucleus. Electromagnetism is responsible for holding atoms together. The balance of attractive and repulsive forces between charged particles is what gives atoms their structure. The negatively charged electrons orbit the positively charged nucleus because of the electromagnetic force. This force keeps the electrons in their orbits, preventing them from flying away. This delicate balance of attraction and repulsion is what gives atoms their structure and stability, forming the basis for chemistry and life itself. Without electromagnetism, the atoms that make up all matter would not hold together, and the universe as we know it would not exist. Scientists continue to study electromagnetism to understand its complexities and to harness its power for new technologies. From medical imaging to wireless communication, the applications of electromagnetism are vast and ever-expanding. As we look to the future, the principles of electromagnetism will continue to drive innovation and shape the world around us. Understanding this fundamental force is key to unlocking new possibilities and advancing human knowledge. Education and research in electromagnetism are crucial for the next generation of scientists and engineers. By studying this force, we can develop new technologies and solutions to some of the world's most pressing challenges. Collaboration and interdisciplinary research are essential in the field of electromagnetism. By bringing together experts from different fields, we can gain new insights and drive progress in ways we never thought possible. Electromagnetism is not just a scientific concept, it's a force that connects us to the natural world. From the light of the sun to the magnetic field of the Earth, it plays a vital role in our environment and our lives. By understanding and appreciating electromagnetism, we can better appreciate the beauty and complexity of the world around us. It's a reminder of the invisible forces that shape our reality and the endless possibilities that lie ahead. Venture deep inside the heart of the sun, where temperatures soar to millions of degrees and the pressure is immense. Here, in this fiery crucible, the fundamental forces of nature come into play in ways that are both awe-inspiring and essential for life as we know it. Among these forces, you'll encounter one that is far weaker than the mighty force of electromagnetism, which governs the behavior of charged particles and the light we see. Yet, despite its relative weakness, this force is indispensable for the very fabric of our existence. This is the weak nuclear force, a subtle but crucial player in the dance of atomic particles. The weak nuclear force operates over incredibly short distances, confined mostly to the realm of atomic nuclei. It is a force that acts on the smallest scales, influencing the behavior of particles within the heart of atoms. One of the most significant roles of the weak nuclear force is in the process known as radioactive decay. This is a transformation that occurs in certain unstable atoms, causing them to emit particles and energy as they seek a more stable state. During radioactive decay, an unstable atom can transform into a different element altogether, releasing particles such as electrons or neutrinos, along with a burst of energy. This process is not just a scientific curiosity. It has profound implications for our world. Radioactive decay is a natural phenomenon that has been harnessed for various applications, from medical treatments to power generation. However, it also poses challenges, such as the management of nuclear waste. Take the sun, for example. The sun's energy, which sustains life on Earth, is produced through a process called nuclear fusion. In the sun's core, hydrogen atoms fuse together to form helium, releasing tremendous amounts of energy in the process. This fusion process is the source of the sunlight and warmth that make life possible on our planet. But this fusion wouldn't be possible without the weak nuclear force. It plays a crucial role in transforming protons into neutrons within the sun's core, a key step in the fusion process. The weak force is carried by particles known as W and Z bosons. These bosons are the mediators of the weak interaction, facilitating the transformations that occur within atomic nuclei. Unlike photons, which are massless and mediate the electromagnetic force, W and Z bosons are much heavier. This difference in mass is one reason why the weak force acts over such short distances compared to electromagnetism. The weak nuclear force may not be as immediately apparent as electromagnetism, but its effects are profound. It is a key player in the processes that power the stars and shape the elements of the universe. Understanding this force unlocks a deeper appreciation of the intricate and delicate balance that sustains life and the cosmos. If the weak force is responsible for the sun's energy, the strong nuclear force is the glue that holds the very building blocks of matter together. This force binds quarks together to form protons and neutrons, the particles that reside in the hearts of atoms. The strong force is aptly named. It's the strongest of the four fundamental forces, outweighing gravity by an astounding factor of 10 to the power of 38 within the nucleus. This incredible strength is necessary to overcome the immense electrostatic repulsion between the positively charged protons packed tightly within the nucleus. The strong force is carried by particles called gluons, which, as their name suggests, glue quarks together. Gluons are constantly being exchanged between quarks, creating a powerful force that keeps them confined within protons and neutrons. Understanding the strong force is crucial for unraveling the mysteries of nuclear physics. It's the key to understanding how stars forge heavier elements in their cores, how nuclear power plants generate energy, and even the very stability of matter itself.